This is going to be the first video of Chapter 14. Chapter 14 is about chemical kinetics. What that basically means is how fast is a reaction happening. So we're talking about rates of reactions. Okay. Now, when we talk about rates of things, if you're talking about traveling a distance, usually what we do is you have your initial point and your final point, and so you can have a change in distance and then you determine how long it took. So, if you're traveling 100 miles and it took you, 50 minutes, you're traveling at 100 divided by 50, which is going to basically be, let's figure it out. 100 miles divided by divided by 50 minutes. You should be traveling about 2 miles an hour. Okay. Well, the problem is that with reactions, things are not moving around like that. That's not really what it means. Okay. So what we do is we measure the change in concentration as a function of time. So in other words, how quickly is a product formed, or how quickly is a reactant used up? It doesn't really matter which one you choose. Okay. So for concentration, it could technically be any of the concentration units, but we almost always use molarity. Okay. So the units on this are going to be moles, it's going to be molar per second. So that's moles per liter per second. We also are going to start relying on this abbreviation thing. A couple chapters ago, I said that we can abbreviate concentration by just writing brackets around it. This means concentration in molarity. And remember that molarity is moles per liter. Okay. So let's just kind of look at an example and see kind of how some of this works, the basics of how to visualize this stuff. So we're going to look at an example. Okay. So let's say we've got C12H22O11, which sounds like this really big complicated molecule. It's literally sucrose. It's table sugar. Okay. If you react this with water in the presence of acid, I'm just going to write it up above the arrow. H plus means acid. We haven't learned about acids and bases too much yet, so we'll get to that later. Basically what happens is this molecule gets split in half and the water kind of gets absorbed in the process. And you form two molecules that seem like they should be the same thing. You get C6H12O6 and C6H12O6. One of these is a glucose and one of these is a fructose. Doesn't really matter for this particular example, but glucose is a 6-membered ring, fructose is a 5-membered ring. So same chemical formula, different structures. Okay. So if we were trying to measure how fast this reaction was going, we could measure how quickly the sucrose is getting used up, or we could measure how quickly the glucose is being formed, or how quickly the fructose is being formed, whichever one. Okay. For this particular example, we're going to look at the rate of sucrose consumption. Okay. And the way we're going to visualize rate is the definition of average rate. It's change in concentration over change in time. Okay. I'm going to just go ahead and refer to this as average rate. It's going to be the concentration of sucrose at time 2 minus the concentration of the sucrose at time 1. So basically, final minus initial. Okay. And the little bracket implies that it is in terms of molarity, divided by the change in time, so T2 minus T1. And what we'll get, the way we usually abbreviate this, is it's the change in concentration of sucrose divided by the change in time. This triangle is delta, it just means change in, okay? We saw it with delta H, we've seen it in other places, but that's what it means, okay? So let's just have some real numbers and some made up numbers, just something to plug in just to see how this works. Okay, so what we're going to have is a table. Okay, so we're going to have concentration of sucrose in terms of molarity, and we're going to have time in terms of seconds. Okay, I guess I could have just left it in S since we were doing that earlier, but seconds, S, whatever. So let's say that at 0 seconds, so before the reaction happened, the concentration was 0.100 molar. Okay, whatever some initial concentration is. Presumably the concentration's going to drop. Okay, so that's fine. The concentration, let's say it drops down to 0.080 molar, and let's say it takes 7,200 seconds. Okay, so our rate could basically be calculated as the change in this divided by the change in this. So we take the second ones minus the first ones, and we get, I guess I probably should point out, if you're using the reagents, this technically comes out negative, and we just put a negative sign in. Basically, we make it positive no matter what. Okay. If it's a product, it's all going to come out positive because the concentration will go up as the time goes up. Here, the concentration is going down as the time goes up, so we need a negative sign. But we're basically just going to rewrite this so that we can kind of watch the process happen. Okay, so we have these values, the final minus the initials, so this would be 0.080 minus, molar minus 0.100 molar, divided by 7,200 minus 0 is 7,200. Okay. If we plug everything in, the rate comes out to be 2.8 times 10 to the negative 6th molar per second. In this chapter, we are going to see a lot of scientific notation because we deal with things that are, rates can be really, really big or really, really small. Okay. So, but this would tell us over the course of 7,200 seconds how fast the rate was changing on average. Okay. The problem is that this is an average rate. Okay. And in the real world, it's a little more complicated than that. So, get another sheet of paper, continue on here. So, in general, no matter what reaction you've got, it's going to look approximately like this. The average rate is always going to be equal to negative delta concentration of reactants divided by delta T, or it's the same thing as the positive change in concentration of products divided by delta T. So basically, because the reactants are getting used up, the negative sign will make it positive. These things, since they're forming, it's going to be positive no matter what. We just need it positive. But either way, you could measure it in terms of reactants or products, but the rate should be the same. Okay. Not a huge deal. Here's the problem, though, is that suppose you were, driving somewhere, and let's say it's 10 miles away. Okay. If you're sitting in your house or sitting in your dorm or whatever, and you go out to your car, and you start your car, and you start the timer as soon as you start the car, and then you drive to this place, you would have the beginning time and the end time, and you would have the total distance between the two. Great, and you could calculate average distance like this. But the problem is at any given moment, you're not going that average speed. You're not going that average rate. In the parking lot, presumably you're not driving 30 miles an hour. You're probably driving like 5, maybe 10. And then when you get on faster roads, you can go a little faster. If you have to stop at stop signs or if you get a traffic light, the speed's going to change constantly. Same is true of reactions. It's not a nice straight average speed like we're depicting it here. So we're going to look at a specific example. This example comes up all the time in this chapter. It's okay. We'll just deal with it. So this is the reaction of H2O2 basically degrading into water and oxygen. The textbook I stole this from wrote it like this and gave it a little half thing, and that's fine. Okay. And what we're going to look at is a graph of concentration versus time. Okay, so concentration going up, time going that way. Okay, So if we did this in terms of H2O2, what we would expect is that because we're starting out with only H2O2, the concentration is going to be pretty high at the beginning, and then it's going to drop. Okay, it's going to decrease over time. But it turns out that it actually forms a curve. Okay, this curve actually tells us a lot about how we should think through reactions for most of this chapter. It turns out that the higher the concentration, the faster the reaction is going to go. And as your concentration drops, it's going to get slower and slower. Basically, the slope of the line is what matters here. So, basically, I guess I'll try to write some of this down here. The greater the concentration, of reactants, I guess I should specify. The greater the concentration of reactants, the faster the reaction rate. Okay. So, but here's the problem. Measuring the average rate is kind of like, you know, if concentration's on the y-axis and time is on the x-axis, this is essentially asking us to solve for the slope. Well, we don't have a line. So, if you're doing something like average rate, it depends on where you picked your data from. Okay, so this is correct, but it's going to give you the average data. So if you pick like all the way back up here and all the way over here, if I had some sort of straight edge, I would make this work, I guess. You're going to get a slope like this. You're going to say, yay, that's my rate. Okay. Slope equals negative rate. Okay. But the problem is if you picked it over if you did the exact same thing but over a smaller time frame, like say we only did the first, so suppose this was like an hour. If instead you did like the first 10 minutes, you're going to get a very different answer. Okay. So the slope of this also is equal to the rate. Which one's correct? Well, it turns out that neither is explicitly correct, unless you are doing the exact same time frame for the same reaction over and over again. So if you were going to consistently do it over the course of an hour, then yes, this is the one you would use. If you're going to consistently do it over 10 minutes, this is the one you would use. But you can't accurately say, for this reaction, the rate is blah, based off an average rate. You can say the average rate is this over that amount of time, but that's a little more, it's a subtle difference, okay? We also could measure this in terms of like O2 production. And what we see is that in the beginning, there should be no O2 at all. But as H2O forms, for every 1 mole of this, you only get a half a mole of O2 forming. So it literally should start at 0, and it should basically go up to about, you know, half of whatever the total concentration was. Okay, so if the blue one is the concentration of O2, you see that we still get a rate, but it's not going to look the same. The rate of formation is going to be literally half of the rate of decomposition here. Basically, this rate is going to fall faster than this is going to rise because for every one of these, you're only making half of one of these. Okay? So it's a little complicated. There's a little bit of subtlety to this. Okay? Typically what we do is we use something called a rate law. And honestly, I think we'll probably wait till the next video to go in excruciating detail on that. All right, thanks.